Good morning, everyone, and welcome again to Chemistry 101. And today we are going to continue with the chapter 8, the periodic table. So last time we talked about the ionization energy and the definition of ionization energy, and we said how there's a trend in the periodic table. Just revise that information again and watch out for the exceptions of the ionization energy that we talked about. Now we define the electron affinity is the negative of the energy change that occurs when an electron is accepted by an atom in the gas state to form an anion. So this is different than ionization energy. This is where the element takes an electron and forms an anion X minus, just like fluorine, when it takes an electron and becomes F minus. So clearly, the electron affinity is something that non-metals would love to do, where metals they don't like electrons. Okay, so we define actually the electron affinity to be the negative of delta H for this reaction. So if fluorine is taking an electron to form F minus in the gas phase, delta H for that reaction is negative value, so that's exothermic. That's something favorable. Okay, that's something fluorine would love to do. And the electron affinity is defined as the negative of that number. So electron affinity for that process is actually plus 328 kilojoule per mole. Oxygen would do the same thing, but with less attitude to fluorine. So oxygen will take an electron to form O minus, and the electron affinity for that is plus 141. So the more positive the electron affinity, the higher the love for electrons for that element. Okay, so fluorine would love to have electron more than oxygen because of its higher electron affinity. So the more positive the electron affinity of an element, the greater the affinity of an atom of the element to accept an electron, or in other way, the energy that must be supplied to remove an electron from the anion. Now, so clearly, non-metals would love to do that, would love to have an electron form X minus, but metals usually they have low electron affinities, and therefore they would like actually to lose the electrons, but not to gain electrons. And here are the numbers. If you see the numbers for the first group, the alkali metals, they have low electron affinities around 60 and 53 for sodium and so on. But for non-metals, especially group 7, the electron affinity is high. It's around 328 in the 300s values. There is an exception. There is something exceptional here that actually group 8 they have negative electron affinities. And that means they totally dislike to have electrons added to them. They're happy. They're stable. They would like no electrons to be added to them, and therefore they have actually negative electron affinities. That means the adding electron would be endothermic for them, actually not exothermic. As we said for ionization energies, we have also some exceptions here for the electron affinity. I'm going to show you that in a second. So if you see this graph here, if you look at the first period, you start with hydrogen, the electron affinity goes to lithium, and then the calcium, which is the beryllium, which is the next element, going up to carbon. Between carbon and oxygen, there is actually a decrease for nitrogen, and this is an exception. And this can be explained in a similar way to the way we explain in the ionization energy. Because of the electronic configuration here for nitrogen, you can draw the electronic configuration for nitrogen and nitrogen minus, and you can see which one is more stable, and that explains the small hump in the ionization energy in the electron affinity trend. Now, so as we said, electron affinity increases from left to right, and that's something reasonable because non-metals would love to have electrons. And the electron affinity of metals are generally lower than those of non-metals, and the values vary very little within a group, and the halogens have the highest electron affinity. So this is just regular true. Now these are the irregularities or the exceptions that we talked about. Electron affinity of a group 2A element is lower than those for corresponding group 7, a group 1A element, and that's because, and the other thing is group 5 has also lower than group 4. So the electron affinity increases as you go from left to right, but there are two exceptions, and these exceptions can be again explained in a very similar way that we explained the ones for the ionization energy. Now, there is a question here that says, why are electron affinities of alkaline earth metals shown table 8.3, either negative or small values, either positive or smaller values? Now, alkaline earth metals are group 2. They have, of course, positive electron affinities, but they have a little bit lower electron affinities than group 1, if you look at the table here. So if you look at lithium and beryllium, the electron affinity should increase as you go from left to right, but actually it's not doing that for group 2. And that's because when you add an electron to lithium, it becomes lithium minus, something that lithium wouldn't do anyway. But lithium minus, the electron affinity of is 60. So lithium has one S1 configuration. When you add electron, it becomes 1s2 configuration, relatively stable. But when you add an electron to beryllium, that will make it 1s2, 2s2, 2p1. So that's adding electron to p orbital would something be unfavorable for beryllium to do, and he would love to stay at a closed shell of 1s2. So this is to explain the irregularities in group 2A, and you have the same thing happening in group between 4 and 5. If you look at the group 5, let's say, if you compare group 4 and 5, the electron affinity for carbon, for example, is 122. You expect nitrogen to be higher electron affinity, but it's 0 because of the same reason here. When you add electron to nitrogen, you add it to you break the stability of nitrogen electron configuration. So just to generalize to finalize this chapter here, we have 3 things we talked about. We have the size, which is the atomic radius. We have the ionization energy, and we get also electron affinity. Radius and ionization energy increases from bottom to top, so from francium to fluorine, and the electron affinity and ionization energy, they both increase from as you go from francium to fluorine. The only thing and size actually decreases as you go from francium to fluorine. So to summarize everything here, we say that fluorine has the smallest size ever, has the highest electron affinity, and also has the highest ionization energy. While francium and cesium in the left bottom of the periodic table, those people, they have very large size, and therefore they have low electron affinity and low ionization energies. Okay, so I will leave you to practice these questions at the end of the chapter, as well as all the questions in the book and the Micro-Hill Connect questions, and hopefully to practice this and score high marks, inshallah, in the final exam. So from here, I will move on to chapter 9 now, unless if you have any questions on this chapter. It's a nice chapter. It's easy one too, and chapter 9 is even easier because you have been you know about Lewis structures and drawing Lewis structures in school, so you should be fine. Anybody has a question? Anybody has anything about chapter 8 or yesterday's quiz or anything? You guys are good? No, there is no صوت بنات. Okay. طيب. So we have 2 chapters left, chapter 9 and 10. We are not gonna. Chapter 10 is only 1 or 2 lectures because not everything is required. But chapter 9 will take. We will spend this week talking about chapter 9. In chapter 9, of course, we're gonna talk about the Lewis structures, ionic covalent bonds, electronegativity, and writing Lewis structure. It's a fun chapter. There's a lot of things to do. Inshallah, you will enjoy it. Now, we talked about this, that elements, they love actually to have a stable electronic configuration similar to noble gases. And Lewis he's an American scientist. He's the first one who postulated that atoms combined so they achieve the more stable configuration that is isoelectronic with a noble gas. So, for example, lithium would love to lose an electron to become like helium. Fluorine would love to have an electron to become like neon. So, and the way you do, and the way that atoms do that is they through their valence electrons. So, whenever you do business with this chapter, you focus only on the valence electrons. Okay, you don't worry about the core electrons because this is how elements they form compounds. So, and group 1, you know that they have 1 electrons in their valence shells, and that's the ns1 electron. So there's having 1. Group 2, they have 2, and group 3, they have 3, the ns2, np1, and so on. Group 7, they have 7 electrons, and group 8, they have 8 electrons, and therefore, mostly, they don't make compounds unless they are in the bottom of the group. Now, what is a Lewis structure? A Lewis structure is basically you draw a dot, okay, or a small circle for each electron in the valence shell. So simply for oxygen is in the 7th group and it has 7 valence electrons on the outer shell, and therefore you can just write 7 dots around oxygen. That's called Lewis structure for that element. Usually we combine every 2 electrons as a pair, okay? Oxygen is a special case here. It's a triplet state, and that's why we draw it this way. But even if you, at this level of chemistry, even if you draw all the electrons as paired, that's fine too. So this is all the Lewis structures for all the elements, and as you see here, oxygen has 7 electrons now. That sulfur is the same thing. Sorry, 6 electrons. Sulfur, selenium, all of that. Group 7, fluorine, chlorine, bromine, they all have 7 electrons in the outer shell, and that is all the Lewis structures for them. So now, now Lewis structures are actually used to predict the type of the bond. So if it's single, double, or triple bond, or whatever, we can know the number of the bonds between the elements, and therefore we can determine the stability of the element. So just to practice this quickly here, suppose that we have a question asking about drawing the Lewis structure for sodium and sodium plus. So we have sodium and we have sodium plus, and I'm interested in writing the Lewis structure of sodium. So sodium is the configuration. So sodium is 11. So it is, if you look at the periodic table quickly, sodium is right here to the left. So the configuration of it is going to be neon 3s1. I'm writing, or 1s2, 2s2, 2p6, 3s1. So it's going to be neon 3s1, okay? That's the condensed electron configuration, or the full one will be 1s2, 2s2, 2p6, 3s1. So here is the valence electrons, okay? We are only focusing on the valence electrons in this chapter. Why this is the valence? Because this is the outer electrons. This is the first shell, n equals 1. This is n equals 2. This is n equals 3. We are only focusing on the valence shells of sodium, and therefore sodium has 1 electron in its outer shell, and the Lewis structure would be something like this. This is the Lewis structure of sodium. You're removing that electron to form Na+, and the Lewis structure for Na+ is this, just simply as this, okay? Sodium, Na, that's it. It's a Lewis structure for sodium. If you want to do it for, let's say, chlorine and chlorine minus, chlorine will have 7 electrons around it, 1, 2, 3, 4, 5, 6, 7. This is Lewis structure for chlorine, and Cl minus would have 8, so 2, 4. Because it has 1 more electron. So this is our Lewis structures for chlorine and so on. So if you have Na plus, which is this, and Cl minus, which is this. Of course, when you do the, sorry, I made a mistake here. When you do this, when you do the lowest structure, you should add the, you do it like that, okay? You should do the, you should show the charge that this is actually an anion. So now we have Na plus, which is this. This is the lowest structure for Na plus, and this is the Cl minus lowest structure. These are cation and anion, and as you know from school, that even positive and negative or opposite charges, they attract each other's, and they form. You're gonna form once these ions they see each other. There's a very strong attraction between this, and this is the definition of ionic bond. Okay, so the ionic bond is between an anion and a cation. Now we explained it based on lowest structures. So the ionic bond is made between metals and non-metals, or basically between an element with a low ionization energy and one with high electron affinity, just like sodium and chlorine. And this is the same example I explained of sodium chloride, but for lithium fluoride. So lithium has 1 electron in the outer shell, fluorine has 7 electrons in the outer shell. If ionization happens, that electron in lithium will fly to fluorine and to form LiF, which is lithium fluoride, okay, where both they have an isoelectronic configuration with helium. So if we go back to our example here for sodium and chlorine, now when sodium lost that electron, okay, to become Na plus, this is isoelectronic now. This is plus, not minus. This is isoelectronic with what? This is isoelectronic with neon, okay? And when chlorine took an electron, now if you look at the periodic table, guess which element he's isoelectronic with? He's isoelectronic with the element next to it, which is argon. So this is isoelectronic with argon. And that's why this is happening, because everybody wants to be a noble gas. Everybody wants to be perfect. So now here, the ionic bond between NaCl is with sodium plus, which is isoelectronic with neon, and Cl minus, which is isoelectronic with argon. And this is the motivation of elements to make bonds. Everybody wants to be a noble gas or have a noble configuration of noble gas. This is another example of lithium and fluorine. When lithium loses an electron, it becomes like helium. Fluorine, when he gains an electron, becomes like neon, and you form the ionic bond between lithium and fluorine to form the salt LiF. So that's the ionic bond. Now, another example of the ionic bond is this example of AlCl3. So aluminum oxide. Now, we said why it's Al2O3, why it's not AlO2, for example, or AlO4, whatever. Al in the third group, he likes to lose 3 electrons to form Al3+, okay? Because by losing 3 electrons, he will become like the nearest noble gas configuration. Oxygen is group 6, that's why he needs 2 electrons to become to the nearest noble gas configuration. So, and therefore, when you're forming Al3+, okay, you have this one at the bottom. If you see the bottom here, you have Al3+. This is the lowest structure for Al. As you see, it's written in between brackets, and they have the charge 3+. And oxygen, this is the lowest structure for O2-. Okay, and when this happens, you will have 3 electrons going from the Al to the oxygens to fill the electrons, and this is how you explain the ionic bond between oxygen and iron. Now, the covalent bond is something different. The covalent bond, there is no actually electrons that going from one element to another. There is sharing of electrons. Because what's happening here, let's take a very easy example of hydrogen molecule. Now, hydrogen has only 1 electron, which is the one S1. Okay. in its shell. There's only one shell. And it's very difficult for hydrogen to lose that electron, actually. Like, to form H+, that's kind of tricky. Because if you look at the ionization energy of hydrogen, it's different than the group 1 elements. And that's why some people, they consider hydrogen even not a metal. They consider it as a non-metal. So it's very difficult for hydrogen to lose the electron and form H+. So that's something impossible. And therefore, what these people will decide to do is they want to come to close to each other, okay? And they will share these two electrons. So if it's better to draw this in different colors here. So if this is the other hydrogen, and now this is the hydrogen molecule. One should be in red, actually. One should be in blue. Now this is the hydrogen molecule, and these two electrons are now shared between the two new atoms, okay? And this is the definition of the covalent bond. The covalent bond is all basically about sharing electrons, but not equally, not one element giving the electron to the other element. So you see here, and we usually represent this with one line. So instead of writing this, we usually write this down, H. So this one dash here means one bond, and it's equal to 2 electrons. So keep this in mind always, that one bond is equal to 2 electrons. This is very important in this chapter, okay? One bond is 2 electrons. So again, the covalent bond is happening between valence electrons, and this is another example of a fluorine F2. So you have a fluorine atom with 7 electrons and another fluorine atom with 7 electrons, and when they form a covalent bond, each one donates 1 electron for sharing, and they make a bond. So I'm going to do it again here for you. So this is the first fluorine, the black one. You have another fluorine, which is the red one. So what these people can do is, this one can share 1 electron, this one can share 1 electron to form the F2 molecule. So this is the electrons. Sorry, I have to keep the colors so you can follow me. So this is the first fluorine with the, and this is the red fluorine. And this is the shared electrons here in the middle, okay? This is the ones that make in the bond, and that usually is written as FF. Okay, you can do that. This is the lowest structure for F2 molecule. If he's asking you to write the lowest structure of F2 molecule, that would be the lowest structure. Now the question is, why not more? Why not? We said that fluorine contributes, each one contributes 1 electron to form 1 bond. Now why not 2 electrons? Why not 3? Why not 4? Why fluorine does not like make this, like three bonds, okay, or 4 bonds? Of course, we're going to come over to this, okay? And there's so many explanations, but the best explanation is that it's because of the Octet rule and the formal charges, okay? As we're going to explain later. So this is the lowest structure of fluorine, as we said. Now we forget to do something here, that we define this. We define. Let's go back to the previous one, sorry. This is the lowest structure for fluorine. Now this pair in the middle, which is this one as well, it's called bonding pair. Bonding pair. That means they are the pair of electrons that make bonding, and this is called lone pair. lone pair. And this question comes all the time. Like, how many lone pairs do we have in F2? We have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. We have 6 lone pairs, a total of 12 electrons making lone pairs. A lone pair means like a couple, okay? So we have 6 lone pairs and we have 1 bonding pair. For the hydrogen, was hydrogen one of theirs? I think it was here. Okay, hydrogen is here. So hydrogen has 1 bonding pair. So this is bonding pair, and number of lone pair equals 0. So number of lone pairs equals 0. There is no any lone pair in the H2. So okay, so single covalent bond, one bonding pair, and this is lone pair. So keep this in mind as well. So for water, as you might know, it's a very famous structure. Water has this structure where oxygen has 6 electrons in the valence shell. It donates 1 electron to the hydrogen. It's sharing 1 electron with the hydrogen, and another electron with the hydrogen, leaving two lone pairs around it, or 4 electrons, and 2 bonding pairs. Okay. Now, of course, this is the lowest structure of water, and many of you might jump and say, teacher, this is wrong. The water, we know the water, it looks like different. So for H2O, we know that H2O actually looks like this. And you are right. And the angle is 109, roughly, 0.5. But this is the VSEPR structure. This is a Whistler structure, okay? And this is chapter 10, okay? But we are in chapter 9, and when he asks you about the lowest structure, you write it like this. Even if it doesn't make sense, but this is the lowest structure. And this is something very, very important that I want to tell you. That for Lewis does not know anything about angles. In Lewis, the angles are either 90 degrees or 180 degrees only. This is a very important rule in Lewis, okay? So if he asks you to write ammonia, for example, ammonia, everybody knows that, and you might study this before. Ammonia looks like this, right? But this is not the lowest structure. This is not lowest structure. If he asks you to write lowest structures, you have to use either 90 or 180 degrees angles. That's it. That's what Lewis knows. So for ammonia, the correct lowest structure would be something like that. Okay, this is the lowest structure of ammonia. Or you can do it whatever you like, but just keeping an angles of 90 degrees and 180 degrees for lowest structures, okay? Even if it's wrong, even if lowest structure does not make sense, but this is the idea of Lewis. Now sometimes compounds are made by having one single bond, like water, and maybe double bonds like CO2 and triple bonds like the nitrogen. Why this is happening? Why N2 looks like a 3 bonds, not 2, not 1. Okay. This all depends on what we call the Octet rule, which is the very important rule in chemistry. And there is also something we call the formal charges. Let's define the Octet rule first, and then we're going to go to the formal charges. The Octet rule, I made it big and nice here in an orange box that says an atom other than hydrogen tends to form bonds until it's surrounded by 8 valence electrons. This is called the Octet rule, and this Octet rule works really well for the elements in the second period. So here we have hydrogen. Don't worry about hydrogen. Hydrogen has only 1 electron, therefore it cannot get even 8 electrons. But for the second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, they must have 8 electrons in their outer shell when they make compounds. Okay? And I'm just going to explain. So a covalent bond forms when there are not enough electrons for each individual atom to have a complete octet. And by sharing electrons in the covalent bond, this will become as octet. So let me explain to you here, through one of the examples that we did, why fluorine, for example, can make single bond, not double bond. Let's go back to fluorine. Now this is the first fluorine, and it has 7 electrons in its outer shell. The atomic number of fluorine is 9, and it has 9 electrons, okay? But the electron configuration is 1s2, 2s2, 2p5. And what we care about here is only the valence electrons, and I want you to keep this in mind, please, when you do this Lewis structures. Now let's bring another fluorine and see what's happening. Now the number of valence electron here is equal 7. And this is that's why this guy is unhappy. Neither this, because they like to have an octet in their outer shell. Octet means 8. And the best thing, as we said, is that when this guy brings this electron to the middle and this electron to the middle to form an F2 molecule, which is again looks like this. Now let's see what's happening here. Now these 2 electrons, which are the bonding electrons, they are shared. They are shared between the 2 elements, and therefore they belong to both of them. So now if you count how many electrons are there for the left element, we have 2, 4, 6, and 8. So 2, 4, 6, and 8. You see how I'm counting this? So now this guy has 8 electrons around it, which means he's happy now. And look at the red element, which is on the right. Now let's count how many electrons it has. Now this one has 2, 4, 6, and also 8. I'm counting the elements on the middle, these elements, to be shared between them. So that means they belong now to both elements. And now it has 8 electrons. So now he's happy. Okay. So F2, we said F2 is a compound or a molecule that achieves the octet rule. Okay, it achieves the octet rule. That means it is good with octet rule, and that's why we draw F2 as this. We don't draw it as double bonds or whatever. Now there is an important rule in this chapter that says CNOF. I'm gonna keep this again over and over. These people they cannot break the octet rule. And this is something really important to remember. It's impossible for CNOF to break the octet rule. It's just difficult for them. Okay, we're going to explain this later why, but just let's remember that. And let's imagine, and to explain this, let's imagine that somebody wants to make a double bond in fluorine. So this is our 2 fluorines again. Okay, you can't replace this with chlorine or whatever. And let's imagine that you want to bring 2 electrons here, okay, to form a double bond. So imagine that you want to do this. That's the first fluorine. He brought 2 electrons to the middle. Now, how many left? So he had 7. So must be 5 here. And the other fluorine will do the same. Okay, so we have 2 bonding pairs and 2 bonding pairs and some lone pairs. Now there's too many things wrong with it. You can draw this as this, by the way. There's so many wrong things in this fluorine. Well, first of all, it looks wrong, but now you want to know why it is wrong. Okay. Now the first thing that is wrong with this molecule is that you have an odd electron here. This is called odd electron. And that is something unhealthy unless you have to. Some molecules, they have odd electrons, but here we don't even need to do that. That's the thing. But the biggest problem with this F2 molecule written this way with a double bond is that, let's count the octet rule. For this, the left fluorine, this is 2, 4, 5, 6, 7, 8, 9. This one has 9 electrons around it because the electrons in the middle, they are shared, and that's why, and therefore they are counting for both elements. So I'm going to do it for the bottom one. Again, this is 2. I want to teach you this, so you do it right, please. How to account for the octet rule, because in the formal chart it's going to be different. This is 2, 4, 5, 7, 9. This is 9 electrons here, 9 electrons here. This one is a wrong Lewis structure for fluorine. You cannot do this. This is unacceptable Lewis structure, okay? It's not even a good, this is, I'm going to write this down. This is unacceptable Lewis structure for fluorine. You cannot do that. It's not allowed, okay? And that's why fluorine has only one electron. And as you know here, even the fluorine that will you have a fluorine 2 minus in that compound, and that's not even acceptable as well. Type. So many of the compounds that you know already, like water and ammonia and methane, they all achieve the octet rule, and that's why they exist the way they do in nature. Look at water, for example. The water has, we said, Lewis structure looks like this. This is the Lewis structure. If you count the octet rule here, you have for hydrogen, how many you think? So hydrogen has 2 electrons around it, because this dash here means 2 electrons, and they are shared between the oxygen and hydrogen. So if you count for the octet rule for the right hydrogen, it's 2, and this one is 2. This one is 2, 4, 6, 8. Again, for oxygen in the middle, it has 2 electrons. These are 2 electrons shared. That means we count them in. So 2, 4, 6, 8, and therefore it's 8 electrons. And you can do this same thing for ammonia and other compounds as well. Now we talked about the possibility of having a single, double, or triple bonds. Now let's take an example of a compound that makes a double bond, which is, let's say, you want to think about CO2, which is carbon dioxide. Now, first of all, you want to decide which atom is the central atom. You can try having this, okay, or this. Now you will discover that this is correct, the correct Lewis structure. And the way you figure this out, which one you decide which one is the central atom, is that it's the atom that can make the more bonds. So which one is the central atom? Because here in the CO2, you might question yourself, which one can we put in the middle? They are 1 carbon, 2 oxygen. Is it like this? Or is it like that? In this case, carbon is the central atom, and in this case, oxygen is the central atom. Of course, this is wrong. And the way you can answer this question quickly by saying that carbon can make 4 bonds and oxygen can make 2 bonds, and that's why carbon we put it in the middle, just without going into much troubles. Now let's try to draw the Lewis structure for CO2. Now carbon, I know that it has 4 electrons around it. Okay, oxygen has 6. And now you want to start thinking about making bonds. The first thing you want to do is you take it step by the time. So you want to take 1 electron first from here. You want to take 1 electron from here to do the sharing, okay? So that will lead you to have this. When the right oxygen gave its electron, now 5 left. Similar here. When carbon gave 2 electrons, now 2 left. There are so many odd electrons here. The octet rule is not satisfied because 2, 4, 6, 2, 4, 6, this is 6, this is 6, this is 2, 4, 6. This is unacceptable Lewis structure for CO2 because it violates the octet rule. This violates the octet rule clearly. Now you should by now know how to count the number of electrons around each atom. For the light oxygen, again, it's 1, 2, 3, 4, 5, 6. Actually, this is 7. 1, 2, 3, 4, 5, 6. This is 7. I'm sorry. This is 7 electrons around it. This is also 7. Let's see how many for the carbon. 2, 4. This is 6. So this violates the octet rule, and the best thing to do in this case is to bring another electron, which is this odd electron here, that is sitting by itself, to be shared with this one, and this one with this one, okay? So that would give you a double bond here, double bond there. This is the very good Lewis structure for CO2. And this one now, 2, 4, 6, 8, 2, 4, 6, 8, 8. This is so CNOF again, CNOF. These are 4 elements that they cannot break the octet rule, and therefore this compound here with a single bond, this is unacceptable. This violates the octet rule. It does not exist this way. CO2 exists in double Y. General rule that carbon makes 4 bonds. Oxygen usually makes 2 bonds, but please don't make the mistake by saying that oxygen makes 2 bonds. I hear people saying that oxygen always make 2 bonds. This is not a rule, okay? And that's not correct. You will have compounds with oxygen making a single bond or triple bond. So that's general rule. There is no rule that says oxygen make 2 bonds and nitrogen makes 3 bonds and so on. The rule is the octet rule. The rule is the octet rule, okay? And the formal charges. I'm just going to explain soon.